Melting, freezing, and sublimation. This involves state changes with solids. So if we think about a solid and the particles are vibrating, as the temperature increases, they vibrate more and more until they are able to break loose and slide around, and they melt and become a liquid. At the melting point, the atoms have enough thermal energy to overcome the intermolecular forces that hold them stationary. Yeah, water melts, ice melts. So here we've got the solid water, and as that warms up, it turns to a liquid. But we have this weird thing that happens with the temperature. When the water and the ice are together, the temperature is 0. Ice water is always 0 degrees Celsius. And it's the same concept as with the boiling. When you're in a state change, all of the energy that's coming in there to melt the ice goes into melting ice, and the temperature of the water will not go up until all the ice has melted. Mixture of water and ice is always going to be 0 at 1 atmosphere. Temperature won't go up until all of the ice is melted. So we can look at a different part of the heating curve where we're going from -20 up to 40 degrees. So here we have solid ice, and we're heating it, and the temperature goes up until it begins to melt. And then it stays at 0. And it stays at 0, and all the energy coming in goes into melting ice until all the ice is melted, and then the temperature can warm up. So when we add ice to something, like there's ice in my drink, why do we put ice in liquid? To make it colder, right? It makes it colder because melting is an endothermic process, and it's going to absorb energy as it melts, and it's going to become colder. Melting is endothermic. That makes sense to us. Just like vaporization is endothermic, you have to put the pot of water on the stove to get the water to boil. You have to put heat into it. That makes sense. To get something to melt, you have to warm it up, right? Freezing, though, is the opposite. Melting is endothermic, freezing is exothermic. When something freezes, it gives off energy. It's crazy to think about. So as the water in your freezer turns into ice, it actually releases energy. And what your refrigerator is doing is it's pumping energy out of the inside of the freezer compartment. So just like we had a heat of vaporization, we can also have a heat of fusion. Fusion is another word for melting. And the way I remember that is, think about chocolate chips. Chocolate chips are good. Put chocolate chips in a pan and you heat them up, and as they melt, they fuse together, don't they? Fusion is melting. So heat of fusion is the amount of heat needed to melt a mole of a solid. Here we have for water melting. It takes 6.02 kilojoules to melt a mole of water. And the opposite is freezing. When we take water in the liquid state and freeze it into the solid state, it releases energy. And this is what I mentioned earlier. Keep your orange trees from freezing. You want the ground to be really wet, to be standing water if possible. Because as the air temperature cools down and that water begins to freeze, it actually releases energy. And it will stay at 0 degrees Celsius until all of it has frozen. That's 32 degrees Fahrenheit. Oranges don't freeze at 32. They have to get colder. And so if you can keep enough water in there, you can moderate the temperature enough to get through the night. So we can use the heat of fusion just like we did with the heat of vaporization to calculate heat to melt something, or the heat released when something freezes. Whoops. So let's do that. Calculate the amount of heat absorbed when a 15.5 gram ice cube melts at 0 degrees Celsius. So what do we have here? We've got 15.5 gram ice cube, that's water, and this is at 0 degrees Celsius. And we want the amount of heat. So something's melting. We're going to need the heat of fusion. So we go back and look that up. The heat of fusion for water, was it 6.02 or 7? Anybody? 2? Thank you. 6.02 kilojoules per mole. So this is going to be a real similar calculation again. We're going to take this mass of water, convert it to moles, so that we can use this conversion factor which relates moles and kilojoules. 15.5 grams of water, convert to moles. This is the third time today we've used that. That's why I've memorized it, because I've done it so many times. And then we're going to multiply by kilojoules over moles. We don't need an equation to tell us what to do. The units tell us what to do. So we get 15.5 divided by 18.02 times 6.02. I get 5.18 kilojoules. Any questions? So this diagram shows us the whole range, going from minus 25 all the way up to 125. And you should be able to look at a graph like this and understand what's going on here. So here, this plateau, what's going on right here? We have ice melting. So we're going from the solid to the liquid state. They're both going to be present here. What's happening up here? Evaporation, boiling. It's going from a liquid to a gas, and so both the gas and the liquid are present. What about in this segment? We've got water that's heating up, but we only have water. And this little piece up here is in what state? That's the gas, and down here, this guy, that's the solid, right? So as we take a solid, like ice, we heat it, the temperature goes up until it reaches the melting point, and then it stays there until it's all done melting, then the temperature goes up again until it boils, and it stays at that temperature till it finishes boiling, and then the temperature goes up again. So when we calculate energy needed, we have a separate calculation for each line. And what we learned to do today was this one and this one, where it's the heat of fusion or the heat of vaporization, and it depends on the number of moles. So if they give you mass, you convert to moles, and then you can find the amount of energy. We did these other parts in an earlier chapter, and that was that Q equals mc delta T equation, where we had the change in temperature. At the boiling point and at the melting point, there's no change in temperature. Sublimation is really a neat thing. That is when a solid changes directly to a gas. It doesn't melt, it just goes from the solid to the gas. And that's not something we see a lot of. And not every substance will do this. But what happens is that the particles, the molecules at the surface, have enough energy to go directly into the gas state. This happens with dry ice or solid carbon dioxide. Dry ice will not melt at atmospheric pressure. You can't get it to melt. It just goes directly from a solid to a gas, which is why it's dry. You put it in your cooler, it eventually disappears, right? But it doesn't leave a big mess, a watery mess that gets your sandwiches all wet. So dry ice, carbon dioxide will begin to sublime at minus 78 degrees Celsius. That's pretty cold. Here's a picture of dry ice sitting in a ring stand. And it's a solid. It looks like snow, but it's carbon dioxide. And this stuff that we see down here, there's the air is being cooled because this is so cold. Cold air falls, and so we see cold air falling here, and this air is cold enough that the water in it is condensing, and so that's why we're seeing kind of a mistiness here. That's not the carbon dioxide. It's actually water from the air condensing on the cold air. That dry ice is pretty fun stuff. Regular ice also sublimes at temperatures below 0 degrees Celsius. We're not familiar with it around here because we almost never get snow. But in cold climates, if you have snow on the ground, even if it's not being melted by the sun, it will eventually disappear. And this also happens in your freezer. I don't know if you've ever had the experience of finding an old tray of ice cubes in the back. And the ice cubes are small. And you're like, what happened? Or maybe some of you remember the Arthur episode where Dora put her snowball in the freezer and then she was so mad at Arthur because he stole her snowball. He didn't steal the snowball. It sublimed. Okay, it just went into the gas state and, condensed other places. It just disappeared. It literally disappeared. This is what happens to the food in your freezer. We don't have tater tots a lot, but occasionally we do. Since we don't eat them a lot, if they're in there, they've been in there for a while. And you open the bag of tater tots and you dump them on the pan. There's the tater tots, and what else? A whole bunch of ice, right? Like, what on earth? Why did they put ice in the bag of tater tots? They didn't. That water used to be in the potatoes, and it's sublimed. Even in your freezer, the water will go from frozen to a gas, and then it'll zing around, and then it will condense somewhere else, and that's where all the frost, or at least some of the frost in your freezer comes from. If you have food in a sealed container, the water sublimes out, but then it can't get out of the container, and so it deposits somewhere else, and that's where you get all the ice crystals that came from your food. So you can get nasty dried out food after a while because all the water, all the moisture comes out and it's nasty. And one thing you can do to get around that is to use there's like a food saver that sucks all the air out, or even just wrapping your food very carefully so that you don't have much air. Because if there's no air in there, there's no place for the water to go into the gas state and move away from the food, and it kind of has to stay where it is. So your food will last longer. Yeah, that's what I was talking about right there. You can read that.